need to let them in, right? I can come back and right. Yeah. So good morning and welcome to yet another online tutorial on principles of communication system. So in last session we were discussing about noise. So we have studied in particular about short noise, thermal noise, and white noise. Right. What we did is we mathematically model different types of noise. Right. Short noise we modeled considering a photodetector, right? So depending upon a randomly impinging quantum of light, how a photodetector emits electrons and how it constitutes a current, right? And because of that random discrete nature of current, right, we have seen there will be short noise, right? And thermal noise, any electronic equipment, right, at a given temperature, we'll have certain vibration of electron within it, and that will constitute a noise. That is actually what thermal noise. And I told white noise, it is an idealized way of modeling any, whatever be the sources of noise, we can model the noise effect in a communication system as additive white noise. In fact, later on we'll study it as additive white Gaussian noise process, right? And we have seen for a white noise, as the name indicates, it has all the frequency components, and the power its mean will be equal to 0, and power spectral density is n0 by 2. All those things we have seen, right? So next we have to move ahead and discuss about noise equivalent bandwidth and SNR, noise figure, all those aspects. But before that, right, before we move ahead and discuss that, I think you should have a clear idea of what is, if you have a noise source, what is the power that noise source can deliver to a system, right? And what is the power spectral density, right? If you give a noise to a particular noise input to a particular system, what will be the output noise, right? What will be the say power spectral density, right? What will be the autocorrelation function? All those aspects we have to learn. So what we'll do is we'll uh, take those things up as some small problems, right? So maybe we'll start with the problem, right? The first problem is, right, it's on thermal noise, right? Maybe you can take down this problem along with me. The mean square value of thermal noise voltage, right? So mean square value of thermal noise voltage So we have represented it as expectation of VTN. Thermal noise we have represented as VTN, right? So expectation of square of this, right? So mean square value of thermal noise voltage, it is given as 4 kT R delta F. So I am using delta F for bandwidth. In some textbooks they are using B, capital B for bandwidth. Anything it will be fine. If it is 4 kTBR or 4 kTR delta F, anything it would be fine. So mean square value of thermal noise voltage, it is given as 4 kTR delta F. Its unit is volts square, right? The question is, what is the maximum noise power it can deliver to any network? Right, so there is some thermal noise source. We don't know what is that. Right, some can be an electrical network or electronic network. Right, so it has a mean square value of this. The question is, what is the maximum noise power it can deliver to any given network? What is the maximum noise power it can deliver to any given network? That is the question, right? So we have represented a thermal noise source, if you remember, as its Thevenin equivalent and also as its Norton equivalent, right? So here R is the resistance, and if this VTN is actually what the so a thermal noise source which produces a voltage of VTN can be represented as its Thevenin equivalent. So R is the resistance of that noise source which produces a noise. Like it can be a resistor or it can be any other electronic component. Right? 1 second, I think someone is trying to join in. I will let, okay, fine. Yeah, so we need to find out what is the maximum noise power if mean square value is this. So this is VTN. So if you are connecting any network, right, any network, we don't know what is that network. Let us represent it as a box, right? A box with some resistance equal to RL. Initially, now we are considering, right? It's purely resistive network, resistance equal to RL. So in this case, okay, again, someone is trying to join in. I might have to let the person in. Right, why you people are joining in late? Right, Shilpa, our class starts at 11:30 and it's almost 8 minutes late. Right, so please try to join in time. Right, yeah. So, uh, the question is, what is the maximum power that this particular noise source can deliver to any given node? Right. So, can anyone tell me what is the answer? Right. Can anyone tell me what is the answer? Right. So you might have studied about maximum power transfer theorem. Right. Maximum power transfer theorem says, right. So any source with internal resistance equal to R can deliver maximum power when this load resistor, right, load resistor RL is equal to this internal resistance. If it is impedance, that load impedance should be complex conjugate of internal impedance, right? So this is the condition for maximum power transfer. So in that case, what happens is whatever be the voltage, it will be divided equally among these two, right? So the voltage across this will be, VTN by 2. Voltage across the load resistor will be VTN by 2 under the condition for maximum power transfer. So Pmax will be equal to VTN by 2, that is the voltage, divided by V square by R, right? Power is V square by R or I square R, right? So power is V square, VTN square by R. We know what is the square of VTN, mean value of square of ETN, right? We know that. So instead of, right, VTN square, we can write, so Pmax is equal to, right, we know the mean value, right? So VTN, it's not a constant, it keeps on fluctuating. We know what is the mean value of that. So instead of VTN as such, we'll be considering mean value of VTN, right? E of VTN square, right, divided by this 2 will be actually what? 4. 2 square will be 4 times R, right? So this will be equal to, we are given 4 K T R delta F divided by 4R. So it will be KT delta for KTB. So this will be the power, right? This will be the maximum power any noise source can deliver to any given network, right? So this maximum power transfer happens when this R is equal to the effective resistance of any given network which we are connecting the source to, right? So that is it. So this is how, this is the maximum power delivered in watts can be considered K, T, and delta F. Where delta F is nothing but what? Bandwidth, right? And T is absolute temperature, and K is Boltzmann constant, right? So this is what is the maximum power a thermal noise source can deliver, right? Now, one more aspect is we have studied something. We have studied about, okay, maybe as a part of next question, right? I'll discuss. So before we move ahead to next question, anyone has any doubt in this first problem? What we have done? Any doubt? It's quite easy and straightforward, right? So, but I have an idea, right? The power being generated within the system, right, and the remaining part of the system can be considered as a load, and this is whatever we found out now is the maximum power the system can deliver, right? So now next question is, show that autocorrelation function ACF. If I write ACF, you have to write, mean it is autocorrelation function of white noise with mean equal to 0 and power spectral density SW of F, right? equal to n naught by 2, right? So I've just discussed it, right? I didn't tell this in detail. I asked you whether you know Einstein-Wiener-Kinjan theorem and all, right? So some of you have replied yes, and some others have told no, right? So the question is, we have to show that autocorrelation function of white noise with mean equal to 0 and power spectral density equal to n naught by 2 is given by Rw of tau is equal to n naught by 2 times del of tau, or you can write Rw of t also, but Rw of tau is equal to n naught by 2 times del of tau. Right, this is what you have to prove, right? So why I have taken up this question is you should be clear with what is power spectral density, right? What information autocorrelation function of a noise process can give, right? You have to be thorough with, right? That's why we have taken up this particular, right? So a white noise means, right, it has, when I say a white noise has power spectral density is equal to n naught by 2, right? Maybe I can visualize it like this or pictorially represent it like this, right? It's power spectral, it is power spectral density PSD, and normally we represent it as SW of F, right? So what is the difference between transfer function and power spectral density, right? So normal transfer function, so we'll represent it as actually what? H of F, right? This will be actually what the Fourier transform of V out by V in, or the Fourier transform of output voltage and output by input, right? That is H of F. That will be actually what in terms of voltage. The magnitude will actually what quantify the voltage, right? In normal Fourier transform, right? If you take Fourier transform of any signal, right, the magnitude will be actually what corresponding to the voltage, but power spectral density is actually what it is, power per unit bandwidth. So this is the power level of each frequency component, right? So if you, what does this mean? It means for all frequency range, the white noise has same power level, right? Whichever be the frequency you are considering, there will be, right, white noise interference. And this n naught, right, this n naught in turn we have represented as actually what? K TE. K is Boltzmann constant, and I have told T is nothing but what? Equivalent noise temperature, right? T is equivalent noise temperature, right? And I have given you the definition of equivalent noise temperature, right? Maybe suppose there is some network, right? Some network, right, which has a given voice output of n out, right? This is the total noise output of this particular system, right? Of this particular system, maybe I'm calling it S, right? So now, what you're going to do, this noise, it can be actually what? Part of it can be, it is generated within it, and there will be some a part of the network which will amplify the signal, so that noise will be amplified, and all those, right, things will be happen. So we don't know, whatever, any the system can be anything. It can be an amplifier, it can be a buffer, or it can be a differentiator, integrator, low pass filter, high pass filter, whatever be the system, right? There will be electronic components, and those components will generate some noise, and also the supply which we are giving also will constitute some noise, right? So this n out, if it is a total noise, so say if you are replacing it with a noise-free system, right? If you are replacing it with a noise-free system, no noise, right? And what you are doing is you are going to connect a noisy resistor, right? You are going to connect a noisy resistor at the input, right? This is noise-free system. This is noise-free system, right? And to the input of the same, right, input of the system, when I say noise-free system, if it is an amplifier, right, a noisy amplifier, exactly an ideal amplifier which is not having any noise should come here, right? I should replace it with a noise-free version of that, and then what I should do is I should keep a noisy resistor at the input, right? Then, and if there is a resistor, that resistor will produce some thermal noise, right? So that the thermal noise will depend upon some the ambient temperature, right? We have seen the thermal noise is 4 kBTR times, yeah, 4 kBTR, right? This is the thermal noise which any resistor will produce, and it depends upon temperature T, right? This bandwidth, resistor K, all others are constant. So it's a function of temperature T. Then at what temperature I should keep this resistor, right? At what temperature I should keep a noisy resistor at the input of the noise free system, so that I will get same amount of noise at the output, right? This noise and this noise are same, right? So this temperature is actually called noise equivalent temperature. This temperature is called noise equivalent temperature. So maybe you just remember this N naught is equal to what? K TE, right? And when you say power spectral density is N naught by 2, it means it has all frequency components in equal amount, right? So yeah, so these are some of the aspects which I wanted to discuss. Now what we need to do is we need to find out the autocorrelation function. So what is given as power spectral density, right? Power spectral density, that is SW of F, is given to be equal to N naught by 2, or it is equal to this, right? SW of F, right? This is F. So this is equal to N naught by 2, right? So now we need to find out the autocorrelation function, right? Autocorrelation function, right? We'll represent it as RW of tau, where tau was actually what? The delay between the signal and itself, which we are considering, right? This autocorrelation function will tell you how two different samples of the same signal will be related, right? If they are um, completely matched, then autocorrelation function will be maximum. If they are completely uncorrelated, autocorrelation function will be, right, minimum, right? So this is RW of tau. Why? It's a property of Fourier transform, right? Property of Fourier transform. We'll call it actually what? Einstein Wiener-Kingen theorem. Correct me if the spelling which I have written is wrong. Right. Einstein Wiener-Kingen theorem. It says autocorrelation function is inverse Fourier transform of power spectral density. Power spectral density. Right. What does that mean? Autocorrelation function is Fourier transform of power spectral density. So now we should find out the inverse Fourier transform of N naught by 2. This N naught by 2, it's a constant, right? Inverse Fourier transform of a constant, right? So inverse Fourier transform of this is what? Autocorrelation function. So you see, it is uh, right, a frequency domain function, which is a constant, which means we have all frequency components, right? There is an equivalent function in time domain, right? There is an equivalent function in time domain, which will give a spectrum like this, right? Which will give a spectrum like this. Can you name the time domain function which has all frequency components? For instance, if you're considering sine 2 pi fct, its frequency domain, it will have only an impulse at f is equal to fc, right? Or else if you take some other function, if it is a rectangular function in time domain, its spectrum will be sync pulsed, right? So can you name the time domain function, right, which when Fourier transform of which will have actually all the frequency components? Can you name that? We have seen this, right? If you can, all of you can type it in chat window. Which time domain function, right, when transformed into frequency domain will have all frequency. Yeah, please, all of you, please do type in. Right, we have, or what is the inverse Fourier transform of 1? Yeah, all of you, please type in. I'll give you 30 seconds. So within that, yeah, I can't see any answer. Right. Oh, no response. And are you able to follow what I'm discussing here? Okay, maybe you don't want to answer. Shall I continue my discussion? Am I audible to everyone? Can you please give me a feedback? Right. Okay, thinking. Okay, great. Yes, yes, fine. So happy that you people are at least thinking. Right. At times, I may feel thinking like what a complete disconnect. Okay, fine. So maybe okay, you don't have to think too much. Right. I'll give you the answer. Right. It will be del of t. Right. An impulse function. Impulse function means right. It is defined only at time instance t equal to 0. Right. And you can see everywhere else the amplitude is 0, and at time instant t equal to 0 the amplitude is almost equal to infinity, right? But instead of telling it's at time instant 0 amplitude is infinity, what we are telling is if you integrate this del of t from minus infinity to infinity, right, the resultant will be equal to 1, or area under this impulse will be equal to 1, and it exists only at instant equal to 0. So the width, if it is almost equal to 0, then the height has to be equal to infinity. So the inverse Fourier transform will be an impulse function. Inverse Fourier transform of a constant in frequency domain. Frequency domain means same value for all range of frequency. It has to be an impulse function, right? So we have actually what inverse Fourier transform of n0 by 2, right? So that mathematically, if we are writing minus infinity to infinity n0 by 2 times e power j 2 pi f tau d tau. Instead of ft dt, I'll write f tau d tau. Why? Because autocorrelation function, right? Always we are expecting the argument of the autocorrelation function as the time difference or time delay between two samples of the same signal, right? So instead of t, right, I am using the conventional tau when it comes to autocorrelation function. If you are using t, right, it doesn't make any difference, right? So this will be equal to what del of tau times n naught by 2, right? So it's very simple. It's right, n naught by 2 you can take out. So it's actually what inverse Fourier transform of 1, right, for all frequencies of f. Then that will be equal to del of tau, right? So I can plot it like this: the inverse autocorrelation function. It will be n naught by 2 times del of tau. What does this mean? What is the meaning of this autocorrelation function as an impulse function, right? Which means, right, if you have a white noise, right, if you have a white noise, it's a completely random signal, right? If it's a completely random signal, right? If a signal is random, right, any two samples you take, right? You take a sample at time t equal to t0 and other sample at t0 plus delta t, right? Whatever be this delta t, right? Those two samples will be completely uncorrelated if it is a random signal, right? So here, what it says is a signal will have similarity with a delayed version of itself if and only if the delay is equal to what? 0, which means a signal with itself, right, without any delay, right? If you take a sample, it has correlation with only that particular sample. Any other sample you take at any given time, different time instance, right, it will not have any correlation, right? It means it's completely random. You can't find any say sort of periodicity, right? Replicating part of type of actually what nature, periodic type of nature, right? It won't repeat, right? So that is what is given by this autocorrelation. So when you say autocorrelation is an impulse function, right? It means the perfect or the ultimate randomness, right? If a white noise, right, it's an ultimate random signal. So when you studied signals and system, you might have studied about actually what deterministic and random signal, right? So this white noise process, it's actually what a completely random thing. Any two samples, however closely spaced they are, or however largely separated they are in time, right? They will not have any correlation, right? It will be equal to zero. It will have correlation. A sample will have correlation only with itself. This is actually what one way of defining it. So we'll for all the cases. So in next case, when you study about actually what output of an ideal low pass filter for a given input white noise, right? We'll analyze the autocorrelation function. Why are we analyzing the autocorrelation function? It's just to see, right, what should be the sampling rate, right? What should be the okay, maybe in terms of sampling rate, when we discuss the next module, we'll discuss, right? So this is how we can find out the autocorrelation function, right? So next question is, right, suppose we have an question 3 is, we have an ideal low pass filter, ideal low pass filter, right? And if you are giving white noise as input to it, right? What is the power output, right? What is the autocorrelation function? These two things are what we have to find out, right? So we have an ideal low pass filter. So maybe ideal low pass filter, its transfer function I can write as h of f, right? Its transfer function will be something like this. If it is ideal low pass filter of bandwidth b, right, it will have frequency contents from minus, it will allow frequency contents from minus b to plus b, and the gain during that pass band, right, will be unity, right? So it is h of f. This is actually what transfer function of ideal low pass filter, right? So this is equal to 0. Now, when you are passing this white noise to through an ideal low pass filter, what we have to find out, what is the power output, right? Also, we need to find out what is the autocorrelation function, right? And maybe before even we can find out what is the power output, we can find what is the, say, output power spectral density, right? What is the output power spectral density? So how to find out this, right? The only thing what we know about white noises, right? So the question is, if you give white noise as input to an ideal low pass filter, what is the output power spectral density? What is the total power output? What is the autocorrelation function? So these are the questions for which we have to find answers, right? So when you say white noise, what are the things which we know about white noise? We know mean mu will be equal to 0, and autocorrelation function SW of f is equal to what? N0 by 2. Other than this, seriously, we don't know anything, right? So these are the two things which we know, right? So then in this case, right, so if you pass, so this power spectral density is actually what? Power per unit bandwidth, right? Power per unit bandwidth, right? So power spectral density will give you the power per unit bandwidth. So this power spectral density is like this, right? So now when you pass it through a filter with this transfer function, right? This transfer function, or this gain part of this transfer function, it is actually what? The voltage gain, right? It is the voltage gain. So we are interested in actually what? Power gain. So the output PSD, right? The output PSD, let it be any system, right? Like we can write S out of F, right? So you can write Sn of F or S out of F, whatever, it's fine, right? S out of F will be equal to input PSD, input power spectral density, time mode of H of F square, right? So this will be output power spectral density, right? So please keep this in mind. We'll be using this relation extensively throughout this module. We will be using this relation, right? So we know the input power spectral density is SW of F, and output power spectral density is S out of F, right? So the input power spectral density and output power spectral density are related as S out of f is equal to mode of h of f square times SWFF. Why? Because it's obvious h of f is actually what the gain as denoted by h of f is voltage gain. So when we need to say power gain, we need to what transform it into power gain. We should square it, even if it is voltage, right? Or magnitude, we have to square, right? So that's why it's like this. So we'll find out now what is S out of F, right? What will be mode of h of f square? So this h of f is nothing but what h of f is, right? We can represent it. It is equal to what 1 from minus b less than or equal to f less than or equal to plus b, and it is 0 elsewhere, right? So this is h of f, right? And SWFF is n naught by 2 throughout, right? SWFF is n naught by throughout. So if you square h of f, you'll get same thing, right? Square of magnitude will be same. So S out of f, so I can write now S out of f is equal to n naught by 2 from minus b to plus b, and it will be 0 elsewhere, right? S out of output power spectral density will be equal to n naught by 2 from minus b to b and 0 elsewhere. So what does it mean, right? So even though the white noise has power component ranging from minus infinity to plus infinity, right? As our system limits actually what the frequency range from minus b to plus b, right? So only the noise within this frequency range will be passed, right? The remaining will be say blocked, right? So now we can draw this S out of f, right? This S out of f can be drawn like this: S out of f or Sn of f, whatever you can, right? So it is equal to, it's from minus b to plus b, and its value is equal to n naught by 2, right? So this is actually what it is, power per unit bandwidth. So total power, right? Total power, P total, right? It will be, total power can be obtained as minus infinity to infinity SW of f df. This is how you can obtain total power. What does it? It's nothing but what total power will be area under this power spectral density curve. It's obvious, right? It is power per unit bandwidth. So if you consider a bandwidth of 2b or bandwidth of this much, right? A bandwidth of, or if you consider only this much part, right? The power within that will be actually what the shaded region. So now the total power is actually what power under this power spectral density curve, right? So that is equal to minus infinity to infinity will actually what reduce to minus b to plus b, right? And it is n naught by 2, right? N naught by 2 times, yeah, n naught by 2 times df, right? So what will be this? So n naught by 2 is a constant, so we can take n naught by 2 out. So it's obvious actually what height is n naught by 2 and length is 2b, right? Height is n naught by 2, length is 2b. So the area is like, we don't have to integrate and all, right? We know how to find area of a rectangle. It's actually what length into breadth, right? So it is n naught by 2 times 2b. It will be n naught b, right? Or else even if you are integrating, so n naught by 2 to take out, it is minus b to b integral df, right? So it is n naught by 2 f b minus b, right? So it will be equal to what? N naught by 2 times b minus of minus b, it is equal to, right? So this is equal to n naught b. So this is the power output. So we got a very important result here, right? Power output. So if you are passing a white noise having power spectral density equal to n naught by 2 through an ideal low pass filter, through an ideal low pass filter, right? The output power is N naught B, where B is the bandwidth, right? Where N naught or N naught by 2 was the double-sided power spectral density, right? So this is the total power. So please do remember this or keep this in mind. So I'll be referring to it when we are discussing about the noise equivalent bandwidth. That is the next section, right? So is this clear how we obtain the power output? Do you still have confusion with the terms power spectral density, power output, autocorrelation function? Please do type yes or no. Right. So I can assure, right. So what exactly is required for your module or the syllabus I'm discussing here, right? And in case if you still have some conceptual lack of clarity, right, maybe we can discuss it later, or you can ask me, or you can even refer to your previous semester video. So I think it's right. It's quite straightforward. So this is actually what the N naught into B is the power. So next we need to find out what is the autocorrelation function, right? Autocorrelation function R out of tau, right? It should be equal to inverse Fourier transform of S out of F, right? It should be inverse Fourier transform of S out of F, right? Where S out of F, what was S out of F? It is equal to N naught by 2 from minus B to B, right? That is equal to inverse Fourier transform of sorry is equal to inverse Fourier transform of right N naught by 2 from minus B to B, right? So how to find inverse Fourier transform? Right, this is equal to integral minus infinity to infinity, right? Or okay, N naught by 2, it should be minus B to plus B, right? Actually, or else I'll write, initially I'll write the equation for of minus B to B, right? So initially I'll write equation for Fourier transform, then we'll substitute, right? So it is minus infinity to infinity, right? S out of F e power j S out of F times e power j 2 pi F tau df, right? E power j 2 pi F tau df. Earlier, if I have written dt, d tau there, when please correct it, right? If I had written d tau there in where when we are taking Fourier transform, please correct it to df. It should be df, right? Maybe if I don't sure, I'm not sure whether I made a mistake, right? So please do correct it. So it reduces to actually what, minus b to b n naught by 2 times e power j 2 pi f tau df. So this n naught by 2 is a constant, we can take it out, n naught by 2, right? Integral minus b to b e power j 2 pi f tau df, right? So integral e power j, right? Integral e power j theta is actually what? E power j theta itself. E power j theta d theta is e power j theta itself, right? So here it's actually what? E power j 2 pi f tau, right? So this will be equal to, right, n naught by 2 times e power j 2 pi f tau, right? Then you have to apply the limit, of course, minus b to b, right? Then it should be divided with derivative of this. It should be divided with derivative of j 2 pi, yeah, this entire thing, derivative of j 2 pi f tau with respect to, or d by df of j 2 pi f tau, right? Derivative of d by df of j 2 pi f tau. So, give me a moment, 1 second. Yeah, sorry. Yeah. So we'll come back to it. Right. So this will be equal to, I'll write here, n naught by 2. If you apply the limits for f, it will be e power j 2 pi b tau, right, minus e power minus j 2 pi b tau divided by df of j 2 pi f tau will be j 2 pi tau, right. So this is what um, we have, right. So now this we can rearrange actually, right. We know e power j theta minus e power minus j theta divided by 2j is actually what, sine theta, right. By this again follows from Euler's equation, right. So we can, so we have 2j, right, e power j 2 pi b tau 2 pi b tau minus e power, so this becomes actually what, n naught by this 2j, let it be here 2 pi tau, let us take here, right. Then e power j theta minus e power minus j theta by 2j, it will become actually what, sine 2 pi b tau, right. It will become sine 2 pi b tau, right. So now what we can do is, you might have studied this in smaller classes, again I'm just right deriving it, right. So we have something sine of pi theta divided by pi theta, it is actually what, we know it's, we can write it as sinc of theta, right. Sine pi theta, it's sinc function you might have studied, right. Sine pi theta by pi theta, sine of pi something divided by pi something, right. So here we have a pi, and with pi we have actually what, 2 b tau, right. Here we have pi, and along with that we have 2 b tau, so we can write it as n naught times sine pi times 2b tau, right, pi times 2b tau. So then in denominator we have actually what, 2 and pi is there, right, pi is there, right, pi is there, 2 is there, tau is there, one b is missing here, right, one b is missing. So if I can introduce this b, if I can multiply and divide with b, right, multiply and divide with b, right, so this will reduce to actually what, sinc function, right, this will reduce to a sinc function. So what we have is, it is n naught b sinc of 2b tau, right. So we can write the autocorrelation function of the output of an ideal low pass filter when input is white noise as n naught b sinc. So maybe I can write it as r out of tau or r n of tau, right. So this is the autocorrelation function. So how to plot this actually? To plot this, right, sinc function, right. Uh, Right. So I'll take sinc theta as example. Right. Sinc theta as example. So when you can see, when theta equal to 0, it will have maximum. Right. And when theta is equal to what, 1, 2, 3, and 4, it will be actually what, passing through the um, passing crossing zeros. Right. So similarly here, right, this is sinc to sinc to beta tau, right. So it, for tau equal to 0, it is maximum, and similarly when tau equal to 1 by 2b, right, 2 by 2b, and 3 by 2b, and similarly for negative values, right, it will be passing through 0. So this is the autocorrelation function R n of tau. This is the autocorrelation function of white noise process, right, as output to a ideal low pass filter, right. So what is the meaning of this? So if you consider, right, so this axis is actually what? Delay. This is autocorrelation function. This axis is delay. So a sample with itself will have maximum correlation, but as you change, right, if you as you take samples at different time apart, right, so if you can see, if you take a samples at distance 1 by 2b or 2 by 2b or 3 by 2b, or in general multiples of plus or minus n by 2b, you can see the autocorrelation will be 0, right? The autocorrelation will be 0 if you take two samples separated by multiples of 1 by 2b plus or minus 1 by 2b, right? So maybe about this, what is the benefit of having a 0 autocorrelation, right? Maybe later I'll discuss, but for the time being, you have to you should be able to appreciate what is its autocorrelation function, right? What is its autocorrelation function? That thing you should be able to appreciate, right? So that is the, so we found what is the right. So we found the output power spectral density, say Sn of f, right, and output autocorrelation function Rn of f, and total power, right, Pn, total power also, total noise power output also we found out in this case, right? So what we found is total noise power. This is an important result. It is equal to N naught times B. It's a function of the bandwidth, right? It's a function of bandwidth, right? This N naught is actually what the N naught by 2 was noise power per unit bandwidth. So this, right, total power is actually what? A function of bandwidth. So that you have to keep in mind, right? So next we'll solve one more problem and we'll wind up this session, right? Q4. So if you are giving white noise to an ideal right RC filter, right? If you are giving it to an RC low pass filter, right? White noise to RC low pass filter, right? So what will be the output? So same thing, whatever we found, we need to find Sn of f, we need to find Rn of tau, right? Not Rn of f. Here also it should have been Rn of tau, sorry, right? And then we need to find total output power. These things are what we have to find, right? So for that, right, if you consider this as a system, an arbitrary low pass filter with impulse frequency response h of f, what is this frequency response? That is the question. So anyone know what is the frequency response of an RC low pass filter? Frequency response is nothing but what? V out by V in, right? V out by V in, and it's Fourier transform, right? It's Fourier transform V out by V in, right? Anyone know? Can you please type it in? Or if, yeah, you can just make wild guesses, not a problem, right? The question is, what is the H of a frequency response of a RC low pass filter? Or should I only discuss? Right. If you want some time to think and write, you can write. Otherwise, if you're not thinking, please do let me know. I'll continue with discussion. Yeah, I can't see any answers. Right. I think I'll only continue with the discussion. Right. So the transfer function, right, H of f of a ideal low pass filter is 1 by 1 plus j 2 pi f r c, 1 by 1 plus j 2 pi f r c. This is the transfer function of ideal low pass filter, right? So maybe you can only find it out. I'll just tell you, I'll give you a hint how to do this, right? So we have an r, right, and c, right? So if you consider this as actually what capacitive reactance xc and this as r, right? So we are giving some input v in here. That v in will be what? Divided between this is open circuit, right, divided between R and XC, right? So this V out, right? So this V out will be nothing but what? V out will be equal to V in divided by R plus XC into XC. So this will be V out, right? So this will be V out. So V out by V in will be equal to V in, oh sorry, V out by V in will be equal to XC divided by R plus XC. And what is this XC? For a capacitance, XC is equal to what? 1 by J C omega, or 1 by J C 2 pi F, right? This is actually what? 1 by J 2 pi F times C, right? So if you solve this, you will get this expression. So please try it out, right? I'm not doing it. You might have studied this in smaller classes, either in network theory or control system. Somewhere you might have studied it already, right? So we have H of F, right? If we have H of F, what will be power spectral density, right? Sn of F will be equal to SW of F into mod of H of F square, right? It will be Sn of F, SW of F into mod of H of F square. It is equal to SW of F into H of F is actually what? 1 by J 2 pi RC. So mod of H of F will be mod 1 divided by mod of 1 plus J 2 pi F RC. Right, it will be equal to mod of 1 by mod of 1 plus J 2 pi F RC, right? So this will be equal to, I'll write SW of F into mod of 1 will be 1 itself. What is mod of, this is A plus JB. It's a mod of a complex number. Mod of A plus JB, it is nothing but what? Root of A square plus, so this entire thing should be squared, okay? This is just mod and it should be squared, right? Mod of A square plus B square, right? So root of A square plus B square. So 1 plus J 2 pi FRC, its mode will be 1 plus 2 pi FRC the whole square, and that entire thing will be under root. So it will be 1 plus 2 pi FRC the whole square, 1 by 2 pi FRC the whole square. So this is the, right, Sn of F, right? This is Sn of F 1 by say 1 plus 2 pi FRC the whole square. Maybe I'll write it down here neatly so that, right, this is one result, right? Sn of F is equal to this SWFF I can write. SWFF is nothing but what? N naught by 2, right? So N naught by 2 divided by 1 plus 2 pi F RC the whole square. This is the output noise power spectral density, right? Now we need to find, next we need to find what is the autocorrelation function, Rn of tau. Rn of tau is nothing but what? Inverse Fourier transform of Sn of tau, right? Rn of tau will be inverse Fourier transform of Sn of tau, right? So that will be equal to, so for this, right, so maybe we'll have to use a standard result here, right? We'll have to use a standard result, right? We know the Fourier transform, right? Fourier transform of, if you take a function like this, right? So this function is nothing but what? E power say minus a mod of t, right? This is t, right? This function e power minus a mod of t, Fourier transform of this function, right? So if, when I say e power minus a mod of t, it means this is equal to, right, for negative values of t, t will be minus t, and for positive values of t, t will be plus t, right? So this will be equal to e power at for t less than 0, and it will be equal to e power minus at for t greater than 0, right? For positive t's, it will be e power minus at, negative will be e power at. It's Fourier transform, you might have studied it, right? E power minus a mod of t, its Fourier transform is equal to, right, 2a divided by a square plus omega square, or a square plus 2 pi f square, right? A square plus 2 pi f square, right? So this is, so now you can see this is actually what almost similar to it, right? But if we do some, we need to get a 2 pi f here. If we need to get a 2 pi f here, what we should do, this RC square we should take common out, right? Then we'll get a 2 pi f, right? So if you take a common out RC square, and if you find its Fourier transform by comparing it with this standard result, right, what we will get is, right, as, right, I'll write it down, Rn of tau is equal to, right, n naught by, say, 4RC, then exponential of minus mod of tau divided by RC, exponential of minus tau divided by RC. So it will be, right, a function like this, and when tau is equal to 0, the value will be equal to n naught by 4RC. When tau equal to 0, the value will be n naught by 4RC, right? And it will reduce to actually what, 0 as time progresses, right? And we have something called actually what, decorrelation time, tau naught, right? So decorrelation time, it is actually what, the time instance at which the magnitude of autocorrelation function falls less than 1%, right? So if this is n naught by 4RC, right, when it becomes 1 by 100th of this, right, when it becomes 1 by 100th of this particular time is actually what, 1 by 100th of initial value of initial, right? That is actually what called decorrelation time, right? And that one, that is equal to what, 4.61 RC. The decorrelation time is 4.61 RC. So we take up all these things at a later point of time as well, right? So now we are just finding out the output possible density and autocorrelation function, right? Right. So that's it. So that's the output possible density and autocorrelation function if you pass white Gaussian noise through a RC low pass filter, right? If you pass it through an RC low pass filter, that will be the possible density. So what this what to say, this HFF of a RC low pass filter, right? HFF of a RC low pass filter, if you can plot it, right? If you can plot it, the HFF of RC low pass filter, it will be something like this, right? Right, HFF of RC, this is actually what, HFF, right? And we have even found the autocorrelation function, okay, output, right? And you know, the 3 dB bandwidth of an RC low pass filter, you already know that, right? Or half power points, it corresponds to actually what, 1 by 2 pi RC and minus 1 by 2 pi RC. All these things you have already studied, right? So this is a 3 dB bandwidth of a HFF. So initially we have seen an ideal filter, right? Now this is a practical filter, RC low pass filter. It has some arbitrary characteristics. It has some upper cutoff, lower cutoff, right? If it was ideal low pass filter, the gain over the range of frequencies which it allows was equal to 1, and abruptly, right, it will truncate the frequencies outside, but in this case it's different. So we have seen two cases. Now by relating these two, in next session we'll come up with the concept of noise equivalent bandwidth, and then we'll move further, right? So that's all about today's session. So if you have any doubt, please feel free to ask. Yeah, any doubt? If any doubt is there, please ask. Otherwise, right. Thank you so much for joining. Right. So no doubt. Right. So my teacher used to tell, right, if you don't have any doubt, it means either you have understood everything, or you didn't even pay attention, or you didn't understand anything. Right. So which is this case? Case one or case two? Okay, fine. Idea. So that's about today's session. Right. We'll okay. At least people are typing in. Thank you. Right. Thank you. Hmm? Yeah. So